Hello, everyone. Uh, like I said in the little introduction there, the main obstacle that programmers face when first learning neural networks is math. Some of us have, let's say, traditional backgrounds like college and that kind of thing. And in that case, you probably can look at like some crazy formula and figure out what it is or what it does. I can't. I don't come from a traditional background. I didn't go to school, etc. And I think lots of us are in that same situation. And then we try to learn neural networks. We look at that, wall of crazy formulas that make no sense and a bunch of like crazy Greek characters and something, and we just run away because it makes no sense. So when I was first learning neural networks, this was a big obstacle to me. So I decided to do this talk and basically show the main concepts of how a neural network works without math, using just code instead. So before we get started, we need to, well, we already did get started. We need to discuss what a neural network is. So I'm just going to go to good old Wikipedia. And we have this here. So a neural network is basically a network of neuron layers, and the vertical lines would be the layers here. And each layer is made of neurons, and they all talk. Now, what is actually a neural network when you abstract everything you can and leave just the one core thing that it does? A neural network is a predictor. It's a thing that you put something in it and it predicts what the output should be. It's also trainable, so it's not like a calculator where every time you type some numbers it gives you an output. It also learns, so it looks at the result it got from whatever prediction it made, it learns from it and adjusts it, and next time it's going to predict a little bit better. So we're going to look at some code. Before we start, just some disclaimers. I'm not an expert in this. I did not do math in college or anything. I just figured this out and I'm explaining to you. I'm a programmer. It's the first time I'm giving this talk, and this is a very complicated subject. So I'm going to be like looking at your faces and see if you're like making a face like it makes no sense, and then try to learn what works and what doesn't when trying to explain this. And feel free to ask questions during the talk. You don't have to wait until the end. If something makes no sense, just raise your hand and something's going to bring the mic to you and you can ask the question. Okay, so let's go back to what a neural network is. We have the network, which is this whole bunch of things that talk to each other, and you forward propagate, you backwards propagate. You probably heard these terms. You have neuron layers, which are bunches of neurons that share the same inputs and outputs. And then you have neurons, which are the main component. So what is a neuron really? And we discussed a predictor. It's something that predicts. So it's something with inputs and that does a prediction. And then we have the neurons. Now, a neuron is very simple. It's just something that takes whatever input it has and multiplies it by a weight. Now, the word weight is kind of arbitrary. I like to think of it as opinion, like this neuron has this opinion about this input, and then it gives you an output. So when we look at how to predict something using just a single neuron, it would be something like this. You take the input, you multiply it by, I should have brought a mouse here. You multiply it by whatever weights it has, which are its opinions, and then you have an output. The number of weights is usually the number of inputs. So in the example I'm going to show here, our data set is going to be cars. So we're going to look at the mileage of a car and how old it is and try to predict its price. So we have two inputs, one output. Since we have two inputs, every neuron is going to have two weights. So I take an input, I multiply it by a weight. I take another input, multiply it by a weight. Then I add the two together, and that's my output. There's also something that you're going to see everywhere when you look into neural networks, and that's bias. So bias is something that's going to take your output and slide it one way or another in a graph. So for example, if you have a sigmoid function, which we're going to look at it soon, it looks like this. A sigmoid, it starts at basically 0, it rises to 1, and then it stays at almost 1. Now, the interesting part in this graph is the bit where it goes, where it rises, where it is like, having change. That part is important. If, because of the configurations in whatever math I'm doing, my graph is here where it is just rising, that is kind of irrelevant. So we want to pan this graph towards the part where it actually changes. That's why bias exists. And a bias is basically you take the result of the computation that your neuron did, and you add the BIOS on top. So it's not gonna, you don't multiply anything or do something that would like change, let's say, the integrity of the result. You just push it one way or another. Something else that we need on neural network, first of all, is to calculate loss. So we need to know basically, okay, I had a prediction. How wrong was this? And to use this, we're going to use a mean square error. And mean square error is, there's a whole thing on Wikipedia about it with like, you know, these things that as you look at it, you can obviously understand perfectly what it does. But what the mean square error is I'm going to take the mean error, and that would be add up how wrong every prediction was and divide by how many predictions I had. We could do that, but the issue with doing that would be if one prediction is off by 1 and my next prediction is off by -1, if I just do the mean error, they're gonna, you know, cancel each other, and it's gonna say, oh, your network's perfect, but it's not. So that's why you use square instead of just mean. So we use the mean square error. And so basically we take the error, we square it, we add up all the, where is it? We have a plus equal here, so we're going to add up into one big value how wrong every single prediction was, and then we divide it by the number of predictions. Let me just check my notes here, and I'm very happy that I have my notes because it's kind of a tradition to me that I make a bunch of notes for the talk, and then like I lose the file 1 second before the talk starts, so I'm happy about that. So now we're going to see this in practice. I have a little example app. Can you see things well there? Kind of, right? Okay, so this is a little example app. It has 4 services. One is the neural network, which is the code that we are going to be looking at. There's a normalized service, which is basically going to take the price of, let's say, a car and take it from 20,000 euros. It's going to put that as a smaller value, like between 0 and 10, or 0 or 1 and -1, depending on stuff. So it's just going to normalize things. Then I have a front end, which is the stuff that you see on the browser, and the console, which is, you know, this like 80s looking command line little tool. And the way this app works is every time I make a change to it, here we're using Garden, which is a tool. Every time I make a change, it's going to rebuild and redeploy my service. So it's going to rebuild my containers. It's going to redeploy those containers onto the cluster I'm using. And sometimes I use like a Google Cloud. This time it's a small thing, so I'm just it's just like a virtual cluster on my computer. So every time I make a change, it's going to reload. We're going to see the results. So if I just save my file here, it's going to detect a change. It's going to rebuild, redeploy, etc. And then this is going to run. And let me look at this. So it's connected to everything. And it has a single prediction, so it's not learning yet. It's just one single point. As you can see here, the predicted values are horrible. So if you want to pay 58,000 euros for a 12-year-old car with 200,000 kilometers, go ahead. So what is happening here? We created a neuron. We added random weights to it, completely random. So we're taking whatever input the network gave us. We're multiplying that input by the weights. We're adding up those results, and that is our prediction. So of course it's terrible because just by listening to how it works, it makes no sense, right? So we need some extra things on this neuron. And now we're going to look at, if I can check my notes. So we're going to have a different kind of predictor because we want this to be trainable. So we need 2 things. One, we need gradients, and the other, we need to change our parameters. Now, gradients are a thing that in math it's called differentiation. And that is, let's say I have any random formula or calculation or computation of any kind. It's a black box. It doesn't matter what it does. I have an input. It does the computation. I have an output. If I change this input, for example, by 1, how much is the output going to change? To calculate that, we calculate the gradients. We do differentiation. Now, this is a very big topic in math. You don't need to be an expert in it to understand how a neural network works. It's just like, for example, everyone can use a calculator and press the square root button. but how many of us actually understand how the algorithm for square root works? I know what it does, but I don't really know every step. So with differentiation, it's kind of the same thing. We can just take it on faith that it works, as long as we know kind of what it's supposed to do. So this is going to do two things for me. One is I'm going to know, okay, if I change this weight on this neuron, how much is my output going to change? And the other thing is, because I know how wrong I am because of the loss function, and by the way, I'm not sure I showed the actual numeric output. So there is a number here for the loss. This is the loss for that one prediction that we did. It's probably 0.4 or something. I should have made just a numeric value visible, but I know how wrong my output was. And so like the big picture is, I know how wrong my output is, and I know how much, I need to know how much changing every little thing inside my neuron changes the output. With that, I can optimize and say, okay, I was wrong by this much in this direction. So I need to take this weight and adjust this one a tiny bit to the left, this one a tiny bit to the right. Then the network improves. I do this 100 times, the network improves a lot. So our neurons now, and by the way, this code is very simple. You just create a neuron with random weights. This tells me how many inputs I have, how many parameters, and parameters are like the bias and the weights. Prediction is the same, but now we have gradients. So we need to understand the bias. It just takes whatever output it is and adds some value to the left or to the right. Minus or add or diminish. So if I change my bias by 1, how much is the output of the neuron going to change? By 1, because it's a 1-to-1 ratio. That's what it does. And if I change, and this is right here, so it's 1. And if I change my a weight by 1, how much is that going to change? So the weight is multiplying the input. So if I change the weight, so my weight is 1, and I make it 2, how much is the output going to change? It's going to change 2 times the input. Can everyone follow this? So the gradients for the weights in this neuron are the inputs. And lastly, we have the input gradients, which we're not going to use right now because we can't change the price of the cars, so the output's not going to change. But if I change the input by 1, how much is the output going to change? It's going to change by the value of the weights, because I'm taking input, multiplying by the weight, and then I have the output. So we have 3 gradients here. The gradient for the bias is 1, because whatever change I make, it's going to reflect exactly on the output. Then we have the weight gradients, which is how much is the output going to change when I changed my weights. And we have the input gradient, which is how much is the output going to change if I change my input. Finally, we have add to parameters, which is just going to take a list of all my weights and add or subtract something to or from them. And now we come to like the big thing in neural networks, which is gradient descent. Now let me show you a picture of what gradient descent looks like. So gradient descent is like this. I have a function that gives me a curve like this, and I know that the point where the amount of loss or error in the network is the smallest, and I want to know like what things do I have to change to make that the smallest. So what's giving me this curve is my loss function. And now I know, for example, if I'm at a point in the curve, let's say I'm on this first point here, I add all my gradients together. I multiply all my gradients together, the gradients that we just saw. And when I know that, I'm going to know the slope of this curve. I'm going to know if I change this whole thing by 1, how much is my output going to change? This is a line, and that line is what's described here. But the thing is, this is not always necessarily linear, so I can't just say, oh, I am wrong by this much, so if in one fell swoop I change all my parameters by this much, then I'm going to go to my optimal point. That doesn't work, because as you can see, the slope here, the inclination of the line here is 1, but the inclination of the line here is different. So I need to take small steps, because where I am right now, if I change things and they go too far, when I get to the other point, things are going to be different there, and it's not going to work. So that's why there's a learning rate, which is a term a lot of you might have heard, which is how far are we going to go on every step. And the thing about this is sometimes if you take depending on how big your step is, you can find the local minimum value of that curve, but then you're not going to find the global minimum value of the curve. And there's the whole discussion about this. I'm not going to get into too much detail because it's complicated. But there's also an issue that if my learning rate is too high, I might end up jumping from one side to the other of the curve, and then I don't go down because I'm not taking steps small enough to end up going to the part where it's actually optimal. So let's run this. So I'm going to save this. Now Garden is syncing that with my little cluster here. And okay, so now I'm running, I'm doing that training that I mentioned, like 200 times or something. And you can see that it basically learned all at once in the first dot there, and then it kind of plateaued and didn't move again. My predictions are, let's say, better. They're kind of random, of course. It's just a single neuron with only the weights and stuff. It's a very simple neuron. But you can see that it kind of learned. It got the results closer, as close as it can, being such a simple thing. So there's a reason neural networks are not like just neurons. It's because a single neuron can't do much by itself. And so we need neuron layers. So now we're going to look at how it would work to have a layer of many neurons working together. Oops, what did I do here? Okay, so we're gonna make a few changes here. This is another iteration of the same code. Now we're gonna have actually, did we add this before or did we add this now? Oh, okay, so one thing I skipped from before is our mean square error function also has a gradient. I forgot to mention. So I take my input, I multiply it by the weights in my neuron, I add the bias, and then I calculate the mean square error. If my goal is to make the mean square error smaller, I also need the gradient of the mean square error. So I can say, if I change something in the network by this much, how much is that going to affect the mean square error? That's going to tell me whether I need the stuff in my network to go up or down. There's a lot of like formulas to calculate this. Like this is, I think it's this one or this one, which is like the differentiation for the mean square error. And again, it's like the square root thingy. You don't need to know exactly how it works. You just need to know. You just need to get what it's like, and then you can just copy some formula, implement it, and it's not going to give you a heartache. Okay, so now let's look at layers. A layer is an array or a slice of neurons. And now we're going to add an activation function. So what's an activation function? As you saw before, that neuron, it was basically just doing multiplication and then addition. That is very linear and very simple. And if you have 100 neurons that all they do is multiply and add, you can just squish them together into one, because it's linear. It's not something. It's something you can simplify very easily. And the things we want to predict are often not linear. For example, we want to predict the price of cars, and let's say in 2011 the car changed to a new model, and then that one is considerably more expensive than the one from the year before. That is not linear. You're not going to have 2008, 9, 10, 11, 12. It's going to be like 2008, 9, 10, 11, 12. So it's not linear, the way things work. So to predict that, we need activation functions that do things that are not linear to our neurons. And we're going to look at this in detail in a minute. For now, so let's just look at how it would work. So this is where we would put the activation function, and I'm going to show it soon. But the way we do this with layers is basically we go through every neuron, we make a prediction, we take the results, and we save them, and that's the output of our layer. For the gradients, it's the same thing for now. We just go through every neuron. We take the gradients of that neuron, we save it. And parameters, the same thing. We go through every neuron. We take whatever parameters we had looked at later for the gradient descent. When we change the gradients times the learning curve, the learning rate, and we just do that, but for a bunch of neurons instead of just one. The activation function, right now, we're just going to use an identity function, which basically returns 1. So we don't need to think about that just now. And the way it's going to run is the same as before. I'm not sure I showed this before, but the way we're running this is we're going through this 250 times. We calculate the mean square error. We do our gradient descent, which is when we adjust the... So we take our how wrong we are, which is what we took from the mean square error, and then we basically make the adjustment to say, okay, this weight needs to go a little bit up or a little bit down to have to diminish the amount of error we're getting. So here we're making a bunch of predictions, which you see the results down here for specific cars, and then they're just sending it over to the network. So this is going to do the exact same thing as before, which is kind of not exciting. Wait, did I change something here? Yeah. Which is going to be not very exciting, but now we have, let's say, the infrastructure to have neuron layers. Oh, it failed. What did I do? I probably changed some single character somewhere here, and then it failed to build. Let's see. Or is it? Oh, it's because I'm not connected to the internet. Can't find the dependencies. Oh, that would be too bad. Anyway, let's move on. So in the next example, I will here. See, that's why I do it wrong, because I type things at random here. Where was I? Okay. So here, on this next version, we're gonna look at using a sigmoid function, and this is a sigmoid function. And the sigmoid function, is this gonna work now? So the sigmoid function is this one, and it takes whatever input you give it, and it turns it into a value between 1 and 0. And it has this curve, exponential curve. And there are many activation functions you can use when working with neural networks. There's like there's a sigmoid, there is ReLU, then there is rectified ReLU, and whatever, there's tons of them. Each works differently. Which one you're going to use depends on the data set that you have. For example, in this case, we want to predict the price. So the price is like a value between 1 and 0, and then I denormalize it, and it gives me the value in euros. I could also do a network that, for example, tells me, is this a cat or not? Or is this a dog or not? And then I wouldn't want something that gives me a random value between 0 and 1. I would want something that says yes or no. And there are many types of activation functions like that. And like I said before, what the activation function does is it takes that linear output of the neuron, like input versus weight, input multiplied by weight, and it turns it into something nonlinear, which is what it's going to do here. It's going to take whatever input it is and turn it into something nonlinear between 0 and 1. We're also going to need the gradient for this, because this is going to be in that chain of operations we're going to do. So we take the input, we multiply it by the weight, then we apply the bias, then we have the activation function, and then we have the mean error. So each of them has a gradient, which we're going to need to be able to adjust the network to make my outputs better. So let's say adjust my weights up or down so that the output is more accurate. So this is the sigmoid function in code. It's again one of those things that you can spend hours like going through Wikipedia and figuring out, oh, so this is why it works the way it works, blah, blah, blah. Or you can just say, okay, I know what it does. I know what the gradient is supposed to do, so I don't need to really go into detail and understand all the details of it. So now we have this activation function, and we put it here on the gradients of the layer. So it's what I just described. We do a prediction that is just like the inputs and the weights and the bias. And then we apply the activation function to make it a nonlinear output. And so that is going to give me my prediction, right? I take the neuron prediction, I apply the activation layer, it's going to give me a prediction. So now I need to go the other way around. So I need to take the gradients all the way back so that I can change my weights and make the network more efficient. So this is what I'm doing here, basically. I take the gradients of my neuron. I take the gradients of my neuron. I multiply it by the gradient of the activation function, and then I add it all up, and that is basically that's what I have. So is this working now? Let me see. Because this one's kind of cool. I want to show you. Okay, so I'm not. Okay, no, this is the layer without the activation function, and you can see it just learns a little bit in the beginning, and then it's fairly linear. So now I'm going to show you what it looks like with the activation function. So Garden's building it. By the way, if you like this workflow where you change your code and it updates everything into your cluster, rebuilds, redeploys for you, etc., do check out Garden. It's a really cool tool, and I would love some stars on its GitHub repo. So if you want to do that, I would be very happy. Anyway, here is the output of our network now. You can see that now it's actually learning as it progresses. So we had 250 cycles there of look at the output, throw it through all that stuff that we showed there, make the output a tiny bit better by the learning rate that is very small, and then check again and see how much better it did. So you can see now that through almost all of the cycles, here at the end it tapered off, but you can see that throughout this process it was learning by quite a lot. And of course my predictions here are still rubbish because this requires some tweaking and stuff. So so it's not perfect. Actually, the output of the single neuron was better than this, but that's how it would work. The thing is, we're using just a single neuron right now, and you would need more of them to make this happen. So okay, we have basically all the main concepts behind the neural network. We know that we know what a neuron is, we know how to put them together in layers. So now I'm just gonna explain to you how it would be to put all of this together in a network. And I didn't prepare the example because I spent way too much time making this look pretty, so I don't have all the code done. But I'm gonna show you, okay, so how do you make a prediction over a network of layers? And this code is a bit clever. It's kind of hard to understand at first, but the way you do it is instead of having the input come from your data set and then you feed that to all the neurons in the layer and then that's the output, what you do when you have a network is you have very many layers. So like this. So you have many layers. So the input for a layer that is not the last one is the first layer is going to receive the input from your data set. The next layer, the input for it is going to come from the previous layer, not from the input of the data set. So you take one layer, you make a bunch of predictions. Those predictions are the input for the next layer. Those predictions are the input for the next layer, and so on until you get finally to the output. And we have to keep in mind the gradients because in a network we need to calculate the gradients. We need to calculate the gradients for the whole network, not just for the layer. So what we did so far is we know the gradients for a single layer and the activation function. But if you have many of those, how do you calculate the gradient for the whole network? And that's extremely simple. You just multiply. Remember when we were talking before of you take the input, multiply by the weight, add the bias, then there's something else that I forgot, and the activation function and the loss function. And so we know the gradients for everyone, and we just multiply them all together to have the result. So this is what we're going to do now. So remember when we looked here, where is this? Here. Here we have the, if I change the input, how much is the output of the network going to change? And when we looked at this, this was kind of useless because we were looking at a single layer, and you can't change the value of the cards. That's fixed. But if my input is going to be another layer, I can change the value of that layer. So if I have the input gradients, I know how much the layer before needs to change so that the output of the network changes. Basically what it does is I'm going to take let's say I did a prediction, okay? I took an input, I fed it to a layer, I took the output of that layer, put it on another layer, and then I took that output and used as like my prediction. So by what we saw this far, I know that the last layer, the gradients of the last layer are going to tell me how much the network result changes, because the output of that layer is the output of the network. If I want to change the output of the network using an intermediate layer, then I need to take whatever gradients that layer has and multiply it by the input gradients of the following layer. This makes no sense, does it? Okay, so the thing is, there is this one person doing something and that causes a result. So if that person changes how they do something, that's going to change the result. Now, if I am the person who gives something to that person and that person then changes the result, then I need to know not only how much what I do changes the result of what I'm giving to the person, I need to know how much what the person is doing is going to change the final output. So to finish this code and make the gradient function for the network, what I would need to do is, instead of just calculating the layer, instead of just calculating the gradient for this layer, I calculate the gradient for this layer and multiply it by the input gradient of the next layer. And then you chain things together and you get the output. And then if you have a network with like 1 hidden layer, 2 hidden layers, 500 hidden layers, it's the same thing. You just multiply all the gradients together and that leaves you to a result. So I have a repo here, a URL. This is empty for now. I didn't have the time to finish this last step that I just explained. I want to finish it before I publish this, so I'm going to put the code there as soon as I'm done with this. And then that's going to give you like how to write the whole neural network from scratch with Go. We got all the primitive parts so far, all the the principal elements that we're going to need. It's not that much work, it's just a little bit complicated, so it's going to be there soon. This is what I had to show you. If you have any questions, please raise your hand or use the app thingy, however that works. I'd like to give a big shout out to my friend Francis Campoy, who helped me with this code. He helped me take it from something that runs to something that's presentable. And big thanks to my company who allowed me to come here. My company is Garden. Once again, if that's your thing, please check it out. Give us some GitHub stars and that kind of thing. And thank you.